All right. Hello, everyone. So we're going to go ahead and get started today. So first out of the gate, there will be a quiz this weekend. Again, Homework 5 was released Friday, or we released Wednesday, so 2 days ago. It is due next Friday. That is the 17th. Um, there will be a Homework 6. It is still being finalized, but just to give you insight into what Homework 6 is going to be, next Wednesday, we're going to be lecturing on linked lists. That lecture is going to be very useful for the first half of Homework 6. The second half will be covered not next Monday, but the following Monday. And then those two lectures will enable you to do that. Skyrim's okay. Breath of the Wild is the most overrated game I've ever played. Um, just just gonna say it, and I don't care. It's incredibly overrated. Um, so today, What is the definition of recursion? Well, the definition of recursion, let's see recursion. And you may think this is a lame joke. Well, if it's a lame joke, by the way, you can see how I play my music now, then why does Google have the same joke? Hang on. Did you mean recursion? Did you mean recursion? Did you mean recursion? Did you mean recursion? I did all of the shrines that I had the patience for, and when they started repeating, I gave up. So I did 7 shrines because they started repeating. That's an exaggeration, but the game sucks. Anyway, I seriously don't like it. Anyway, um, so today we're going to be talking about recursion. We're going to do some examples of this. If you've not seen recursion before, you will see it now. All it is a self-referential process. So when we're talking about algorithms, we're talking about um, defining a problem by breaking the problem down into simpler versions of itself. And we have a couple examples of this later. It sucks is too strong, but I seriously did not enjoy finishing the game. I didn't at all. Um, so recursion is often a very natural way to express an algorithm, and it turns out to actually be quite useful here. So generally, when we're talking about recursion, we want to focus on a few things. First, we want to look at how do we take a complex problem and break it into 2 or more smaller problems, or sometimes just 1 or more smaller problems. How can we do that? So if you've taken, for example, 2102 discrete math, or you're taking it now, you may have seen something called proof by induction. Proof by induction is very, very tightly tied to recursion. The two very closely relate to one another. And so we want to look at how can we take a problem and break it down into smaller problems. And then at core, what we want to identify what is called the base case of a problem. And the base case of a problem is kind of a root, almost axiomatic truth. That is to say, at bedrock, we start at one point, and then using recursion, using our recursive solution, we can build upward from there. So an example of recursion, and we're actually going to get into this next Wednesday. We're going to talk about linked lists and how they're actually implemented. I know I've talked about them before, but we're actually going to implement one. A recursive definition, it can be defined in mathematics as a self-referential process, and we'll do an example of this later, where n factorial equals n times n minus 1 factorial. Further, we have a recursive procedure, a procedure that calls itself, etc. So, the simplest example that I can think of for this, and let me move my bald head over here. I would ask that after class, and I'll be happy to answer that question. I just don't want to interrupt lecture right now. So Towers of Hanoi is a classic little game, and the goal is you have 3 pegs, you have some discs. If you've ever played a BioWare game from the early 2000s, you invariably saw this. And the idea here is this game involves moving all the discs from this peg over to the peg on the right, as you see here. But you have certain rules. You can only move 1 disc at a time. No disc can be placed on top of a larger disc. And the key is, again, you have to move every disc to the left. And so let's actually play this real quick and do Towers of Hanoi. By the way, you can see my cheat codes. I just use YouTube for the music for games, except for Fire Emblem. I actually do have the soundtrack to that game. So let's say I were to play Towers of Hanoi with 3 discs. So the goal is I want to move all these pegs over here, all these discs, excuse me, over here to over the right side. So I'm going to start by moving disc 1, disc 2, disc 1, disc 3, disk 2, and there we go. That's the simple solution. But I want to take a minute and break down how this solution works. First, I want you to notice there are 4 disks. And the way that I'm going to solve this problem is I'm going to move 4 disks to the left. And by the left, I mean it goes left and it wraps around and comes over here. That's what I mean by the left. Think of this as right, wraps around, and comes back to the left. Left from the left, wraps around, comes back to the right. So we're going to start here. And I'm going to start by, if I need to move 4 disks to the left, I'm going to start by moving 3 disks to this peg on the right. So how am I going to do that? Here we go. I have now moved 3 disks to the right. That was my first step. And now you may be thinking, wait, you've done 7 moves. For now, just think of this as a step. I move 3 disks to the right. I then move my 4th disk to the left. And now I move these 3 disks once again to the right. Again, while I'm doing multiple moves here, think of this as a single step. What I have just described is actually a recursive solution. And here's how we can define it. First, I have n disks on this left peg. I'm going to move n minus 1 disk, that is every disk but the bottom one, to the right. And I'm going to end up with this image over here on the right. I'm then going to move the bottom disk to the left. And I'm going to move n minus 1 disk to the right. Now, given this solution, how can I move n minus 1 disk to the right? I could apply the same solution to say, first move n minus 2 disks to the left, move the n minus 1th disk to the right, and then move n minus 2 disks to the left again. The reality is this solution scales all the way down, and I can repeatedly use this. And it turns out that I can actually implement this as follows. Here is code that will take in a number of disks, and it will tell me the moves to make to play Towers of Hanoi in the optimal fashion. And I have written this code, counting white space, counting closing brackets in 20 lines of code. And this will solve every Towers of Hanoi problem. First, I have a number of disks I'm moving. I have a Boolean for left. I'm either moving to the left or the right. So Boolean makes sense here. If this is true, I'm moving left. If this is false, I'm moving right. If n equals 0, well, how do I move n disks? How do I move 0 disks? Let's play, and it won't actually let me do it, but how would I play if I had 0 disks? How would I play Towers of Hanoi? And I'm done. I don't need to do anything. Right? I don't need to move any disks if there are none. So, if I have 0 disks, return. I'm done. Otherwise, I'm going to move n minus 1 disks in the opposite direction. So for example, if this is false and I'm moving to the right, not left would be true, which would mean I would be moving to the left. So it's always n minus 1 in the opposite direction. Then I move the nth disk. And the way I move the nth disk is I print move disk number n. And it's either to the left if left is true, or to the right if left is false. Then from there, I move n minus 1 disks to the left again. To run this program, and I actually have to, first I need to set up a run configuration. I can pass in a command line argument. We haven't gone over this in class before yet, so don't worry if this doesn't look familiar. But let's say I had 5 disks. I now run this program, and this set of instructions will tell me exactly how to play Towers of Hanoi with 5 disks. If you follow these directions, you will win Towers of Hanoi in the smallest number of moves possible. And there it is. And this would work for any number. Now, there's a myth, and let's hope it's a myth because it sounds pretty dire, that somewhere on a mountaintop there are three there's a group of monks that are constantly playing Towers of Hanoi, and they have 64 golden discs on 3 diamond pegs. And the myth goes that when they finish that game, the world will end. And so the question is, and this is a very important question, will we ever see Winds of Winter by George R.R. Martin, or will the world end first? And given that, we can actually calculate the number of moves it takes to play. See, the thing is, if I play Towers of Hanoi with 1 disc, it takes clearly 1 move. But if I play Towers of Hanoi with other disc counts, let's say I have 3 discs, or 2 discs. Well, if I have 2 discs, and this is my number of discs and my number of moves. Clearly, if I have 1 disc, I just move the 1 disc. I'm done. From there, if I need to move 2 discs, I have to move 1 disc twice and the disc number 2 once. That takes 3 moves. If I have 3 discs, I have to move... Sorry, let me get that out of the way. I have to move 2 discs twice. So 2 times 3 is 6. Plus 1 to move that disc, 7. The formula, it turns out here, is 2 to the power of n minus 1. And 2 to the power of 64 is a really big number. For context, 2 to the 30 is roughly a billion. It's actually, it's a bit more than a billion, but roughly 1 billion. 2 to the 30 squared would be a billion squared, and we would still need to multiply that number by 16. So, what would it be? A billion, a trillion, a quadrillion, a quintillion? So it would be over 16 quintillion steps. And if you do the math on that, it works out to, and I'm not great at math here, it works out to a really big number. It's something like, several hundred billion years. Yeah, and the minus 1 is important. It's several billion years. Hang on, let me actually work it out here real quick. 2 to the power of 64 minus 1. That is this many seconds. Divide that by 60. This many minutes. Divide it by 60. This many hours. Divide it by 24. This many days. Divide that by 365.24. And that is this many years. So, given that it will take this many years for the universe to end, that is, let's see, that's thousands, millions. So 584 billion years. I regret to inform you that while we will get Winds of Winter, Dream for Spring will not be published by the time the world ends. Anyway. Point being, it would take a really long time. But I want to work out the mechanics of this code, because this introduces something new. First, let's look at main. Main, all this does, this gets the number that I put in my command line arguments. It turns out, actually, this is true. It turns out that the estimate, 600 billion years, is actually close to when the Stelliferous period will end, which is to say that our universe will not be producing many new stars at that point. Almost no new stars. So, in some ways, that is kind of the end of the universe. Anyway, space. Anyway, I then just call move n, and I'm moving n elements to the left. You remember that video, I'm glad. So, let's actually look at this function. This moves is the name of the function. It takes in an n, and it takes in a boolean. Well, what function am I calling here? Moves n minus 1. Oh, wait, I'm calling this function. A function calling itself, can it do that? Well, yes it can. I actually don't, that message was not, that message was okay. Please don't, just because that was a reference to a video that I actually posted about exponential growth, which dealt with the universe death clock, so please untime out that user. No worries. I appreciate the aggression because it's gotten bad before. Um, all right. So now, this is a new thing, a function calling itself. And the problem is, if a function calls itself, couldn't that lead to an infinite loop, or what we would call infinite recursion? And the answer is yes. So therefore, at some point, we have to have something that terminates this loop. In this case, somewhere where the loop ends. Specifically, I say, if n equals 0, return. This is called, and this is a very special term, my base case. And the base case means this is some bedrock principle that I am building my recursion on top of, which is to say, this is the simplest version of the problem my code can solve. And the simplest version of Towers of Hanoi I can solve is 0. You may think, well, 1 is also pretty simple. 1 requires effort. I have to move a disk from all the way over here to all the way over here. That takes work. That's way too much work. 0 is so much easier because it takes no work at all. So 0 is my base case. And by the way, that code will be uploaded later today. Another example of recursion is factorial. So let's take a look at that. With factorial, and I'm going to write this in a bit of a weird way. The idea of factorial, understand that factorial is not just some quaint mathematical thing. Factorial actually has a very, very practical application. For example, let's say I have this USB battery, this glasses case, this eraser, and these 2 markers. So I have 5 things. And my question to you is, if I were to arrange these things, and I'm hoping they won't fall over, how many ways could I arrange these 5 things left to right? Well, I could pick any one of these 5 to be the first element. Then I could pick any of the remaining 4 to be the second element. Then any of the remaining 3. Then any of the remaining 2. Then any of the remaining 1. This is 5 factorial. So factorial is not just some quaint mathematical concept. It actually is a very, very straightforward application of combinatorics. That is how we can arrange things. But let's actually take a look then at some examples of factorial. Well, so for instance, I might have 5 factorial. That is going to equal 5 times 4 times 3 times 2 times 1. I have 4 factorial. Actually, I'm intentionally going to do this way. 4 times 3 times 2 times 1. 3 factorial. 3 times 2 times 1. 2 factorial. 2 times 1. And 1 factorial. 1. Here's a question. What is 0 factorial? Well, to answer that question, I currently have 0 things here. How many ways can I arrange these 0 things? That way, 1. I have 1 way to arrange these 0 things, and here it is. Isn't it glorious? So this actually does equal 1. Anyway, I want to point out, and some of you may find this trivial, I want to point out something. 5 factorial is 5 times 4 times 3 times 2 times 1. What's unique about this? Well, it's the same as 4 factorial, right? And 4 factorial is 4 times 3 times 2 times 1. What's unique about this? It's the same as 3 factorial. And 3 factorial. 3 times 2 times 1. Same as 2 factorial. Such that any number, n, factorial equals n times n minus 1 factorial. But this isn't true for every number. Can anyone think of a number where this is not true? There we go. OP Flowers got it. This is not true for 0. 0 factorial, we've already said, is 1. Does that equal 0 times negative 1 factorial? I don't even know what negative 1 factorial is. How do I arrange negative 1 things? How do I even show negative 1? Do I just like pull the whiteboard off the wall here? I don't want to do that because I just bought this house. that would be pretty catastrophic. So this doesn't hold true for 0. And coincidentally, 0 is my base case for factorial. So now let's take a minute and let's write a factorial function. And for now, we're going to make this static. Public static. And I'm actually going to use long. And the reason I use long, an int, the maximum value of an int is roughly 2 billion. You can actually get the max value of an int with system.out.println integer.maxint. But it's roughly 2 billion. And 2 billion, it turns out, is not that big a number. There's more than int number of people in the world today. So any numbers larger than that, you want to use long. So I'm going to use a long. And this is going to be public static long factorial int x. It's going to still take in an integer. Actually, let me change this to n for the sake of simplicity. And generally, again, most cases are going to look like this. Return n times factorial n minus 1. This is a self-referential process. It's exactly what I wrote at the bottom of the whiteboard. N factorial equals n times n minus 1 factorial. The recursive methods don't have to be static. This one is static because I'm not creating an instance of the class recursive function. So I'm not creating an instance of this class. I'm just going to call this function like it's a library method, so that's why I'm making it static. I could make it non-static. It just, I don't have any instance variables or anything, so there's no real benefit to me making it non-static. I've written many recursive functions that are not static, for the note. When we get into data structures, we'll probably write one or two. But again, this doesn't always apply. This applies, sure, for 5, 4, 3, 27. But it doesn't apply for 0. And so what I need to do is I need to select out, if n equals 0, the base case. And if I have the base case, if n equals 0, then I'm just going to return my bedrock truth. That is my predetermined value of 0 factorial. Otherwise, I calculate this. And I want to illustrate how this recursion works. System.out.println entering factorial plus n. From there, I'm now going to say system.out.println returning from factorial. Well, actually, let me do it this way. I'm going to say long result equals that, and then return result, and then system.out.println returning factorial plus n. And what I want to illustrate is how this works. And so, public static void main string args system.out.println factorial, let's go with 6. And if I run this program, I get the correct result, which is 720. But I want to illustrate how this worked. So I entered 6 factorial first. That called here 5 factorial. 5 factorial called, again here, 4 factorial. 4 factorial called here 3 factorial, which went here. 2 factorial, which went here. 1 factorial, which went here. 0 factorial. And 0 factorial just returned 1. From there, once 0 factorial returned 1, we went back up to factorial 1. We then plug in, okay, factorial n minus 1 was 1, so result equals 1 times 1. Factorial returning n, and I'll even add here result plus result. And let me just show you what this looks like. So notice here the value of result was 1. We return that value of result to 2 factorial. So 2 factorial was 2 times the previous result, 1. So 2 times 1 is 1. It's 2 times 2. 2 times 1 is 2, excuse me. So then from there, I return this value 2 to factorial 3. So that's 3 times 2, which is 6. Return it 4 times 6, which is 24, and so on. And if you'll notice, and thank you, I don't know how to pronounce XA, but let's just go with Dash for short. Dash pointed out, hey, this looks kind of like a stack, doesn't it? I mean, let's remember what we talked about with a stack. Zadash, got it. A stack is first in, last out. What was the first function we called? Entering factorial 6. What was the last function to finish? Factorial 6. And so if you actually look at this visually, what you'll recognize right out of the gate is we end up with a stack kind of like, and let me move once again. I'm once again asking you to move my fat head out of the way. We can see that we get kind of this pattern here, where each function is combining these elements, and we end up with building up this stack until we get to our base case, 0 factorial, which lets us finish calculating this function, which returns here, finish calculating this function, return here, finish calculating this function, return here, and so on. And so, the base case of n factorial is 0. McBurney said, yeah. And so, the idea is we generally always put the base case first, and we select out for it. And we select it generally with an if statement. In recursion, very often you will see selection. That refers to deciding whether or not you're in the base case, and recursion. Why is nothing being returned each time the print statement showcases the result? It is being returned. It's being returned after the print statement. So I return result, and so I'm printing the return value here. So that we start factorial 6 first. But before factorial 6 can finish, we can't answer what factorial 6 is until we know what factorial 5 is. Well, notice down here, we find out that factorial 5 is 120. And so that returns and allows us to determine factorial 6. Of course, it's not as simple as just figuring out what is factorial 5. In order to figure out factorial 5, we need to figure out factorial 4, which is here, factorial 3, and so on. And so we start factorial 6 first, but we finish factorial 6 last. And once again, that is first in, last out. So this behaves like a stack. And in fact, whenever we've talked about calling functions before, go back to when I talked about pass by reference when it comes to Java arrays, for example. I talked about the stack and the heap and how function calls go on the stack. So this isn't actually new. Now, is recursion more efficient than a loop? So this is where technically everything that can be written in recursion can be written as a loop. But some things are much, 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 much easier to write in recursion than in a loop. An example of this would be drawing a tree where you have one branch that splits off two branches, that splits off two branches, that splits off two branches. That can actually be tricky to do with a loop. I've tried to do it and gotten stuck. It can be done, but it's tricky. For instance, this Towers of Hanoi problem. I don't know how I would write Towers of Hanoi as a loop here. Now that I think about it, I'm starting to think of a couple ideas I would use. But it would certainly be more difficult. It would certainly take more effort from a programmer perspective. Now, the solution with a loop would actually be more memory efficient, but it would be not any more runtime efficient. Because the problem is Towers of Hanoi is an exponential problem. The problem can't be solved faster than exponential time. That's because the number of moves you take grows exponentially. Right. So understand, recursion is not something that we're telling you should use from now until the end of time. You are all Batman. And one of the tools on your utility belt is a batarang. But you should not use the batarang to climb buildings. The batarang won't help you climb buildings. You need the grappling hook to climb buildings. Recursion is just a tool in your arsenal. It is not something that you will just always use from now until the end of time. So recursion does, because we're adding things to the call stack, recursion does add memory. So you can run into issues with recursion if you're not careful, where you do run out of memory. That can happen. An example of this is, let's say I accidentally do, and I'm just, and this is nonsensical. I don't know why I would ever ask for factorial -3, but let's actually run this, and what you'll see is this crashes, and the crash message is this: at recursion factorial, all of these line 8s. This is me here. I'm scrolling the mouse wheel as fast as I can. I'm really trying. And if you look down on the bottom right, you can almost see the mouse wheel moving. And if I just click and drag this, I got down to factorial -5066 before my program crashed due to a stack overflow error, which again, function calls go on the stack. And what this means is that we ran out of memory. So that can happen. If you did a loop, you wouldn't run into this issue. So because a loop doesn't constantly add memory to the stack like function calls do. So there are disadvantages to recursion. But again, recursion does allow for some code to be written more simply, more understandably. And also, I want to be clear, recursion is an idea. You don't actually have to explicitly call a function itself to do something recursively. Could you call factorial 5066 then? Let's find out. I'm going to comment out my print statements for this, because I don't want my print statements getting in the way. I actually think the limit would be 5063 since I started at -3, but let's find out. Keep in mind, the result won't be correct. 0. Okay, I want to explain why we're getting 0 here. Because this is a bit weird. First, to explain this, I need to change this value to an int. And I want to show you why we don't use an int. Factorial 13 is a really big number. If I have... Oops. What did I not like? Wait. Right. Factorial 13 is a really big number, but that is actually not the correct number. I know that's not 13 factorial. And there's a simple reason that I know this. 13 factorial would involve multiplying by 10, right? What is the last digit whenever you multiply by 10? It's 0. So why is that not 0? It's because factorial grows so fast that when you do have factorial 10, you're already looking at 36 million, or 3.6 million. Factorial 11, you're looking at nearly 40 million. Factorial 12, you're looking at 479 million. This number times 13 is greater than 2. Or, excuse me, greater than 2 billion. It's also greater than 2. But it's greater than the maximum integer value. And so what happens is integer.max value plus 1 equals integer.min value. And it's just because it will wrap around. And so, according to Java, whatever the int cap is, roughly 2.1 billion, that plus 1 is negative 2.1 billion. And if you ever want to see an interesting story, look up, it's related to this, the Gandhi civilization bug. So if you've ever played Civilization, you will know that the leader most likely to use nuclear weapons, no matter what, is Gandhi. And if that seems anachronistic, it is. And it was the result of a bug. Now they do it intentionally because it's funny. But the original game, Gandhi was the leader that would be the most likely to use nuclear weapons, and it had to do with an integer underflow error to his aggression score. So you can look that up on your own time. I don't want to take class time to describe it. You can have more than one base case. Briefly, we can describe Fibonacci. Have you guys ever heard the joke about the Fibonacci sequence? Anyone? It's as good as the last 2 jokes you heard put together, I swear. All right, that's it. I gotta end the stream now. Bye. No. Sorry, I apologize for that. So, with that, the Fibonacci sequence, if you don't know, is this. And by the way, the Fibonacci sequence comes from a monk watching rabbits reproduce. So it's weird. Anyway, initially your Fibonacci sequence is 0 and 1. And the next number is determined by adding the previous 2 numbers. So 0 plus 1 is 1, 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5, 8, 5 plus 8, 13, and so on. And by the way, it turns out that there is a closed form expression to find a value, and it's something like the root of 1 plus square root of 5, I can't remember the exact value. It's something, it involves the square root of 5, like 1 plus root 5 over 2 to the power of n plus 1 minus root 5 over 2 to the power of n. I think that this is what it is, but I'm not going to claim certainty. You can test this out in your own time. There is a closed form expression. This number, by the way, is called phi. Just this to the power of 1. Anyway, if you ever hear phi in mathematics, that's what it comes from. So from there, in order to build this, we could build this very simply in a recursive way. Public static long, again using long for the same reason as before. By the way, if I go back and change this out to long, you'll see that the result is actually fine at that point. If I put in a long, I'm getting that 4 billion number that I expected to get. Anyway, so public static long fib, because Fibonacci grows fast as well. Int n, typically this will equal return fib n minus 1 plus fib n minus 2. However, we need a base case. As we said before, looking back at the whiteboard, my first two numbers were 0 and 1. So we can start if I, and by the way, there's some inconsistent definitions here. Sometimes you'll see people say fib 1 is 0. Sometimes you'll see people say fib 0 is 0. Sometimes you'll see people say fib 0 is 1. For sake of this lecture, I'm going to assume the first number is my 0th number, and the second number is my 1th number. Anyway, so if n equals 0, return 0, but I also need to isolate the second base case. Else if n equals 1, return 1. And technically I could just do an if. I don't have to do an else if, but whatever. And if I call this, and I call fib 12, you'll see I get this number, which works out pretty well. And if I call fib 20, 6,065, okay, that's fine. And if I call fib 30, you'll notice something starts to happen here. Let's go to 50. Wait, where'd my number go? What is happening? Well, here's what's happening. And that's why it's going to take a while. What is happening is this. The way I'm solving Fibonacci has an inherent flaw. And by the way, as soon as it finishes, I will tell you. I will go back to the screen. See, if I'm solving, let's start with just Fibonacci of 4. Fibonacci of 4. Well, to do that, I have to make two function calls. Fib 3 and fib 2. And by the way, it's not done yet. Oh, it just finished. So this is how long it took. It just finished. And if I did Fibonacci 100, it wouldn't finish today. Anyway. From here, well, how do I solve fib 3? Well, I make a call to fib 2, and I make a call to fib 1. Okay? Well, fib 1, I can stop here because I know fib 1, I just hit return. But fib 2, I need to break up to fib 0, or fib 1, excuse me, and fib 0. Similarly, I need to break this fib 2 up the same way. Fib 1 and fib 0. And it turns out that if you look at this, you'll start to notice a pattern emerge. How many times do I call fib 4? I call it 1 time. How many times do I call fib 3? I call it 1 time. Fib 2, I call it twice. Fib 1, I call 3 times. What if I were to do fib 5? Well, if I were to do fib 5, I would need to call fib 5 1 time. That would split up into 4 and 3. I already have a 4 here, so I would call fib 4 1 time. But I'd end up calling, because I'd have this whole tree and this tree duplicated, I'd call fib 3 twice. I'd end up calling fib 2 3 times and fib 1 5 times. Oh, hey, anyone see this sequence before? Anyone ever see that sequence before? I can't recall. That is the Fibonacci sequence. And as a result of this, the number of function calls I have equals the sum of all the Fibonacci numbers before it. And as a result of that, the number of calls I make here is actually bigger, or it ends up being about this many calls to the function. Yeah. It's bad. It's really, really, really bad. It's a really bad way to do Fibonacci. So what we could do, and by the way, you could do this with a loop, but we're going to do this with something called tail recursion. I'm going to cheat. int result. And you may be thinking, wait, but I don't know what the result is. How am I passing it as an argument? Stick with me. Actually, I'm going to be honest. I'm not going to do tail recursion here. I'll do tail recursion on factorial probably on Monday. I don't want to get into tail recursion yet. Yeah, I don't want to get into because I'm talking about that Monday. I will do a Fibonacci with a loop real quick, and the loop is as follows: so static long fib iter, and that's short for iterative. Int n. Do you have a quiz this weekend? Yes. And to do this, I'm going to define long result equals 0. And then from there, actually, I'm going to say long result equals 1. And I'm going to say if n equals 0, return 0. So I'm still going to separate that out from the rest of the loop. Long previous equals 0. And then from there, while n is greater than 0, while n is greater than 1, I'm going to do the following. I'm going to say long temp equals result plus previous. Previous equals result. Result equals temp. Return temp. Excuse me, not return temp. Return result. And if I do this correctly, and it's possible I didn't, so stick with me. If I do fib iter 50, remember this is the recursive version we got. I should get the same number. Let's make sure we don't forget. Let's copy that to a notepad. Oops, I'm still calling. Oh, I accidentally. Sorry, I forgot a critical step. N minus minus. Now I actually have an infinite loop here. Now I don't. There we go. Look at that. I got the same result. Look how much faster that was. And the reason relates to algorithms. Hang on. Loops are not always better than recursion. I want to be very clear. You can do, by the way, you can write a recursive solution that is just as fast as the loop. It's because of the way I wrote my loop. And the way I wrote my loop, this function is O of n exponent. This is to say exponential. It's O of n squared. And the proof for how this is O of n exponential is complicated enough that I'm just not going to do it. That's fair, Zadash. This function is, by the way, O of n. And linear is substantially better than exponential. You can do an exponential recursion. It involves something called tail recursion. But from there, we're at time, and I don't want to go too far down recursion today. But from here, that's actually, you're prepared now to do the homework, because we're not doing anything too advanced with the homework with recursion. Sorry. I did this wrong. It should be 2 to the n. Sorry. This is exponential, because it turns out that Fibonacci is exponential. Fibonacci is, the Fibonacci value is phi to the power of n, so technically this is phi to the power of n, but you can say it's proportional to 2 to the n because of logarithmic math. So I did mean exponential. Sorry. Is the factorial recursion? No, this is linear. This is in fact linear, and it's because the number of calls I make is proportional to the value of n. So actually, in this case, a recursive or a iterative solution would have the same runtime. They would both be linear time. The key that causes the problem with Fibonacci is the branching calls. It's the fact that I have branching calls that makes it exponential. If I didn't have branching calls, and by branching calls, just to clarify what I mean, notice that fib4 calls two functions. That's what makes this exponential. If it only had one call like factorial, it would be linear. All right, I'm going to wrap it up there. Any questions today? Could you store all the fibs you've already calculated in memory to speed it up? You could. Um, what I would say is there's such a thing called memoization, and that it's spelled weird. It's something I'm not going to teach in this class, but I teach it in my other classes. And the idea of memoization is that you store results. So if you've asked a question before, like if I've asked at some point in the previous like fib 10, I'm going to save that result somewhere in memory. So that way the next time I see fib 10, I don't have to calculate it. I can just get it. And that is trading off time for memory. I have to store that, so it costs me memory, but it saves me time. Can you scroll down to fib iter real quick? Yes. Here. Here is all your Fibonacci needs in one screen. And notice that this is O of n fairly trivially. This one you should be able to look at and see it's O of n. Here, this is not the easiest thing to look at and see it's exponential. Just trust me, it is. But yeah, that's actually a common technique. It's also a technique for you can use it to determine as efficiently as possible all the prime numbers from 1 to some n where you store lists. Can you show us cats? Yes, I can. 1 second. So Morgan Kitty doesn't tend to hang out when I'm talking. Morgan doesn't really like loud noises, and my voice carries. But Stewie and Colby are kind of used to Daddy's loud voice because I've had them for, well, Colby 7 years, Stuart 6. But anyway, there they are. Oh. Colby is on top of the couch. Stuart is sleeping. They're both sleepy boys. They sleep snuggling together most of the time. Like, they actually sleep, like, literally wrapped up in each other a lot. They are adorable. And yes, that is a shirt because I live in squalor. So, this is kind of like a little basement room that is in my house. And I just put all my old furniture that I'm embarrassed to be seen with down here. Are Valorant drops enabled? No, I've mentioned this before. I really suck at shooters. I suck at Overwatch, and I don't even know how you can suck at that game. I'm good at MOBAs, but I really suck at shooters, so I don't think I'm gonna get into Valorant. Um, I tend to actually be a healer main. I'm a Mercy, Lucio, and Mariah main. How does recursion work with immutable data types? You can still do so with immutable data types, what you're actually doing is you're returning a different instance, but it can still work. So with the palindrome, you're returning a string, but you're still just looking at the contents of the string. Remember that when you say, so for example, if I say string s equals cat, and then I say s plus equals s, that makes it where s is in fact cats. The string has changed. The difference is this may have a memory address like 46AB731. This memory address will actually be different. It may be something like that. It will be a different memory address. Do you play 2K? Which one? Does that mean I play League? No. I actually I take that back. I suck at most MOBAs. I play Heroes of the Storm because it's the casual MOBA and it only takes 15 minutes for a game. Where League takes what, like 4 hours? I think like right now they're still playing League games that started before coronavirus. I'm pretty sure. No, I don't really play basketball video games because they're kind of RNG based. There has never been a game of Monopoly that's finished. Anyone who tells you otherwise is lying. Do you have a console? I have several. That's why I have two TVs. Because the big TV there, sorry, it's weird because it's mirror image. Or it's not a mirror image, it's a flip image. The big TV there is for my modern consoles, and then the little TV there is for my older consoles, like my GameCube and that. Yeah, you may not have gathered this, Black is Basic, but I was kind of trolling. And if you think, wow, that guy's kind of sarcastic, blame my stepfather because that's where it came from. I do actually own a PS4, but I don't play it much. So I mostly play PC. I do have a Switch too, and the Switch is awesome. The Switch is amazing. Yeah, it turns out that I actually don't think games of League take 4 months. I who knew? Skyrim's okay, but I mean it's been almost 10 years. Play a new game. How much time does CS 2150 really take? I actually don't know. I've never taught 2150. And I've only been here. This is only my first year here at UVA. My understanding is a lot, but I can't give a meaningful estimate. Wii Sports. No, I don't have a Wii. I refuse to have a console that I can't say the name of with a straight face. So I like Hearthstone Battlegrounds, I would say, but I don't really like Hearthstone. I don't have a problem with Minecraft. I'm just bored of it. Like I killed an Ender Dragon. That's the end of the game, right? Moving on. You know, I killed an Ender Dragon like 6 years ago or something. Any Zachtronics? Can't recall. I'm not familiar with the name Zachtronics. Yeah, but that's the problem, Keens. I don't have friends, so how am I supposed to play Minecraft multiplayer? That is mostly sarcastic, by the way. But I don't really have friends who play Minecraft. Um, I just like for me like so they are billions. I haven't played the campaign. I got really good to where I was winning like 70+% of my games on 800% on They Are Billions. And so I got bored with it, and every time I think of like, oh, I can go back and play the campaign, I never do. I mean, I don't have time. Like I've been trying to finish Dragon Quest 11 for like a year and a half now. And I'm like, I think I'm like maybe 3/4 of the way through the game. I don't speed run games. I've tried. I honestly gave it a shot when I was in grad school, and I just don't have the patience for it. Portal 2 is the best design game ever. Portal and Portal 2 are amazing games. Portal 2 is the best design game ever. I don't really play shooters. That's the thing. Like the last shooter I played reliably was Modern Warfare 2. And every time I've tried to play a shooter since then, I've sucked so bad that I've not enjoyed it. Actually, no, I take that back. I played Black Ops 2 a lot. I did play Black Ops 2 a lot. But not on PC. I think I got Black Ops 2 on PC as like a gift from someone, and I'm like, dude, I don't really want to play it. I played it mostly on Xbox 360. I don't like card games. I mean I like Hearthstone Battlegrounds because I can watch Netflix while playing it. I don't remember. I never played Black. No, wait, no. I take that back. I own Black Ops 2, but I did not play Black Ops 2 multiplayer. I only played Black Ops 1 multiplayer. I take that back. I never really played Black Ops 2. I think I played through the story, maybe. But yeah, it was Black Ops 1 was the last like Call of Duty game I played. And it was really the last shooter I played multiplayer in. Again, I don't play much Overwatch, and that's like the one I've played the most in the last few years. All right. By the way, like if you have a serious question, I will answer that first. I want to be clear. Um, all right, it's 1 o'clock. I actually have a ton to get done today. I got to get a quiz up in my other class, so I'm gonna do that. Have a good weekend, everyone. I'll see you back on Monday. Take care.